Alright, today we're going to be going over vector spaces and how to calculate if something is in a vector space. So to start, we're going to go over what a vector space is. A vector space is a collection of vectors that can be added together and multiplied by scalars and have certain properties. And these properties are called axioms. And we're going to go over them today, but we have axioms 1 through 10. And to start with the axioms, we're going to go over the most important ones, which are the ones you'll check first, which are axioms 1, axiom number 6, and axiom 4. So axiom 1 is closure under addition, which states that if a vector u and a vector v are objects in the vector space of v, then the vector u plus v is in v. So if we had a vector, which let's say is 4 and 4, and that's our vector u, and we have our vector v, which is 2 and 2, and we said that our vector space v means that it is all real numbers, then u and v will be in the vector space because they are a part of the all real numbers. And we know that if we add u plus v, that will give us our new vector of u plus v, which will give us 6 and 6. And since these are both real numbers, we know that this will be in that vector space as well. Our next one that we're going over is closure under multiplication, which if our vector u is in the vector space and k is a scalar, which just means any number, then k multiplied by the vector u must also be in the vector space. So we'll go over to how to test these ones later, but what that means is if we have our vector u again, which is 4 and 4 from before, and we'll have the same vector space of v being all real numbers, then what we could do is we could have a scalar k, which we could call 2, and as long as this is still in the vector space of all real numbers, then this vector is also in the vector space, which would give us 8 and 8, which is still both real numbers, which means that it is in the vector space. And finally, our last one that is the most important is the existence of the zero vector. So what this one means is there exists an object in V, our vector space, called the zero vector that is denoted by the 0 with an arrow on top and has the property that 0 plus the vector is equal to the vector plus 0 for all u in our vector space V. So what this one means is if we had our vector of 4 and 4 and we added 0 and 0, then this would be the correct zero vector because it gives us back 4 and 4. So all this means is under whatever condition of our vector space, our zero vector is whatever gives us our original u vector back. Alright, now we have the rest of the axioms. So our next one is the associativity of addition, which means that if you have a vector u plus a vector v plus another vector w, in order for this axiom to be true, it has to be the same in the vector space as if the vector u plus, in brackets, vector v plus the vector w, just meaning whatever way you add all your vectors together, the order shouldn't matter. And next up is the commutativity of addition, which states that the vector u plus the vector v is equal to the vector v plus the vector u, which means that the order of how you add your vectors shouldn't matter. Next is the existence of the additive inverse, which means if you have a vector u, there should be another vector in the same vector space that is negative u, such that if you add them together, you'll get the zero vector, which is just all zeros. Next up is the distributivity of scalar multiplication, which means for all scalars of a and b, which again are just two random numbers, and all vectors u and v, it is stated that a or b multiplied by your two vectors added together will give you your scalar multiplied your first vector plus your scalar multiplied by your second vector. Now we have the distributivity of scalar multiplication with respect to field addition, which is the same thing as the last one we did, but instead of the two vectors being added before you add the scalar in, it's the two scalars being added together before you multiply them by your vector. Our second last one is the compatibility of scalar multiplication, which is that if you have k as a scalar multiplied by a scalar m multiplied by your vector u, is the same as the two scalars being multiplied by together multiplied by your vector. And finally, the existence of multiplicative identity, where you have 1 multiplied by your unit vector, 1 multiplied by your vector, just gives you your vector back. Alright, now we have the vectors u is equal to 1 and 2, and our vector v, which is equal to 3 and 4. And now we're going to try to see if they fit into the vector space, where the vector space is all real numbers. So the first thing we're going to do is test to see if it is closed under addition. So all we have to do is we have to set it up as u plus v, which is equal to 1 and 2 plus 3 and 4, which gives us, as we just have to add our x values together and then our y values together, this will give us 4 and 6. And since 4 and 6 are both real numbers, this one gets a check and this axiom is satisfied. Next up, we're going to check under scalar multiplication. So this is going to check that k and u, as well as k and v, both fit into the vector space. So first up is k and u, and we're going to just pick any scalar k. Alright, we're going to have k and u and k and v. So we're going to set up as k of 1 and 2, and we're going to have k of 3 and 4. This will become 1k, and this will become 2k. And then this will become 3k, this will become 3k, and this will be 4k. And since any value of k here will get you a real number in return, no matter what, if you multiply it by 1, 2, 3, or 4, which means this axiom is also satisfied. So next up, we're going to test our association of addition, which is the u plus v plus w is equal to u plus v plus w. So if we have our u and v, our u is 1 and 2, and we're going to add 3 and 4. And as long as we pick another vector in the same space, which we'll just say is w, which is 1 and 1 for this example, we just have to make sure this is equal to 1 and 2 plus 3 and 4 plus 1 and 1 first. Well, this one will give us our same addition as question 1, which is 4 and 6, plus 1 and 1, which will give us 5 and 7. And then our right side is going to be giving us 1 and 2, plus 4 and 5, and then we added our 1 and 2 to give us 5 and 7, meaning that this axiom is also satisfied, as they are the same. So next up is the commutativity of addition, which means that u plus v is equal to v plus u. So we're going to have 1 and 2 plus 3 and 4, and we're going to see if that is equal to 3 and 4 plus 1 and 2. And this will give us 4 and 6. And on the right side, we'll see that it also gives us 4 and 6, meaning axiom number 4 works as well. So number 5 is the existence of the 0 vector, which means that we have 0 is equal to 0, 0, and that u plus 0 is equal to 0, which works in this case because if we have 1 and 2 and we add 0, 0, that will give us 1 and 2 in return, meaning this axiom works as well. Next up is our number 6, which will give us the existence of the additive inverse, which means that if we have a u, there's such thing as a negative u, which will give us 0. So to test this, what we're going to do is we're going to write out our u as 1 and 2, and we're going to write our negative as -1 and -2. And as long as this gives us 0, 0, then this axiom works as well. Now we have number 7, which is the distributivity of scalar multiplication, which means that if we have a scalar a and our vectors v and u, so u and v vectors, that a multiplied by u plus v, both vectors, is equal to AU plus AV. So if we set A to any random number, so we'll just keep it as A, and we'll just say that it's A is equal to any random number, then we can have our A multiplied by 1 and 2 plus A multiplied by 3 and 4, which will give us 1A and 2A plus 3A and 4A. And since A is a real number, and we already know that it's closed under addition, meaning that U plus V works together, that means since A is a real number and the addition of U and V is a real number, then this all is a real number, meaning axiom 7 works as well. Now next up we have axiom number 8, which is the distributivity of scalar multiplication, which is for any scalar A and B, and a vector U. A plus V multiplied by U is the same as A multiplied by U plus B multiplied by U. So if we set A as a scalar, which will just be A for us, and B is B, but A and B are both real numbers, then we know that A plus B will also be a real number. We know that A plus B is going to be a real number, and we know that U, the vector of U, is a real number, and we know that U is a real number, which means that a real number multiplied by another real number gives us a real number. So that means that this AU plus BU is also going to be a real number, meaning it fits our vector space and it fits our axiom. And the axiom is satisfied. Next up is our second last one, which is the compatibility of scalar multiplication, which means that if we have our scalar A and B, and we have our vector U, then we will have A multiplied by B multiplied by U is going to be the same thing as A multiplied by B multiplied by U. So if we have A and B again is a real number, and A and B multiplied by together is also a real number, and we know that U is a real number, and we know that from earlier that multiplication of two real numbers is also a real number, then three real numbers multiplied together will still be a real number, meaning that it fits our vector space and the axiom works. And finally is axiom number 10, which just states that 1 multiplied by our vector U gives us U. And if we have our 1 vector, which is just, if we have 1, which is our scalar, multiplied by our vector 1 and 2, even if you multiply it in, it still gives us 1 and 2, meaning that all the axioms are satisfied. U and V satisfy all 10 axioms, meaning that they are in the vector space. Alright, and our final question for today is we have the vector U, which is 0, 0, and the vector V, which is 1 and 2. And our vector space for this question states that U plus V is equal to U1 plus V1 plus 1, and U2 plus V2 plus 1 for our Y. And K multiplied by U is equal to KU1 and KU2. So whenever we're trying to see if it satisfies the other equations, or the other axioms, we have to implement these as well. So we're gonna try to test it for axiom number 7, which is KU plus V, which we're gonna see if that equals to K multiplied by the U vector plus K multiplied by the V vector. And how axioms work with proving if something's right or wrong. For proving something right, you normally have to try to use it in variables, since it could have infinite amount of numbers, such as real numbers, it's infinite. While if you want to prove something's wrong, all you need is to have one counter argument, and that's all you need. So if you can find one axiom that fails, then your whole thing could fail, and you don't have to check any other axioms unless the question asks you to. So for this question, we have K is equal to 2, and we have our U and V up at the top. So what we're going to do is we're going to test our K multiplied by U plus V, which will give us 2 multiplied by our U plus V. But if you remember our U plus V from up top, it's not just regular U plus V. We have to have U1 plus V1 plus 1. So we're going to have 0 plus 1 plus 1 and 0 plus 2 plus 1, which will give us our new vector of 4 and 6. Now what we're going to do is we're going to try it this way of having K multiplied by U plus K multiplied by V, which will give us 2 multiplied by 0 and 0, plus k multiplied by 1 and 2. This will give us 0 and 0, plus, our k is 2, so this will give us 2 and 4. And then when we add them together, we'll have our 0 plus 2 plus 1, and we're going to have 0 plus 4 plus 1, which will give us 3 and 5. And 4 and 6 does not equal to 3 and 5, meaning that k of u plus v does not equal ku plus kv, which means that axiom 7 fails. And therefore, u and v is not a vector space with this condition.